Yes, Shikha students, let's start with class ninth work and energy. All right, uh, students, let's start with understanding of what is work, what are the units of work, and how do we define the basic unit of work. Now, students, let's say this is a table. On this table, we have some book. We apply some force F here. Let's say F is 5 Newton. I, I think we know that the unit of force in SI System International, is Newton. Now, as a result of application of this force, let's say the book moves from point A to point B. Alright, as a book moves from point A to point B, it covers a distance of, let's say, 2 meters. Alright, now somebody says, how much work is done? How much work is done by the force F on the book? So, see, now in order that work is done, book should move. So basically we are applying force. We are applying force. Force, think what would be the formula to calculate work done? What are two important things in calculation of work done? One, force should be there. Force must be there to move some object. Without force, a object cannot move. Very simple. But then at the same time, if there is a wall, this is a wall, this is the foundation of the wall, no matter how much force you are applying, the wall will not move. It might break at larger forces. But let's say there's a human being and he's applying force, gradual force. No matter how much force a man applies on this wall, the wall is not going to get displaced. If the wall had been displaced by a distance of d, we could have calculated work done. But the wall is not moving. So we understand that work is done as a result of work done, something is getting displaced. In other words, we can also say something is getting accelerated. In other words, we can say, let's say a vehicle is moving. Let's say a vehicle is moving in this direction. Now we apply braking forces. Braking force by the brake leathers. There are brake leathers which apply the braking force in the opposite direction. So what happens here? The body is not getting accelerated. Let us say the body is getting retarded, and eventually it stops. Its velocity becomes equal to 0. It comes at rest. So either the force is accelerating something, or the force is retarding something. Either it's increasing its velocity. See, in this case, the velocity initially is 0. And when you move this ball, it acquires some velocity, some value for velocity, let's say x meter per second. In this case, the velocity is decreasing. So in both the cases, acceleration is there. So force applied is displacing a body. In this case, we say work done is not there because the wall is not moving. So from all this discussion, from all this judgment, what do we understand? That work is done if there is force. And what is the second parameter?
Distance.
Beautiful. There is distance. All right. Right now, we are not going in the nitty gritties of whether it is displacement or vector product or dot product, which we will be learning in further lectures or higher classes. So, force and distance are two quantities which decide whether a work is done or not. And in physics, we say force multiplied by distance, students, is the work done. Now, having understood this, we can very well answer there is force here, but D is equal to 0. That is the reason work which is equal to F into D. Force is there, but D is not there. We say work is 0. Here, the work done is negative. Why? Because in the direction of applied force, this is the direction of applied force, in the direction opposite to the motion of the car. The motion is happening in this direction, but the force is applied in opposite direction, right? So the work done is negative. In the case when force applied and the distance or the displacement of the body are in the same direction, we say work done is positive. Work done is equal to 0 in two cases. What are those two cases? Work done is 0 in two cases. Either there are two parameters for work done, force and distance, force and distance. So either when I say the work done is 0, either when force is equal to 0, yes students, or when
Distance is equal to 0.
when distance is equal to 0. Wonderful. Now let's think about a practical situation where force is equal to 0 but distance exists. The body is traveling, not r, s. Distance is there. And let's talk about a situation where distance traveled is 0. Distance traveled is 0 but force exists. Means force is being applied, but distance is 0. A person trying to move a wall, and there's a big mountain, all right? A person applies some force on the mountain, the work done is 0. Work done is 0, all right? There's a car, you're trying to move the car is so heavy, you're not able to move the car, work done is 0. Can you think of any situation where force is equal to 0 but distance is there? It's an ideal situation. Ideal situation means, let's say this is the ideal plane. What do you mean by ideal plane? An ideal plane has 0 friction. An ideal plane has 0 friction. It's perfectly polished. The surface of the body is also 100% smooth. There's no friction. There's no air drag. There are no external forces being applied in opposite direction of the motion. Let's say we have a shining ball. The ball is rotating and at the same time moving in the positive x direction. Positive x direction. Now, since there is no friction between these two surfaces, there are no frictional forces which normally act in a direction opposite to that of motion. In this situation, remember first law of motion. The first law, which is valid only on the surface of Earth, states that a body will continue to move till infinity unless and until it is compelled by some external force to change its state. Right now, the body is in state of motion. The body is moving. When it is moving, its state of motion is not going to change. And we have assumed there's no air, there's no frictional force, there are no viscous forces, nothing else in the opposite direction. So, in this case, displacement is there. S's exist, but there is no force acting on the body, as a result of which the body has a motion. Then can any student tell me why the body has motion? There is no force being applied in this idealistic case. Idealistic case. This is an idealistic case. It's a, it's a, it's you can say a theoretical case. It's not a practical case. Practically, there'll be so many forces: frictional force, air drag, viscous forces, or some irregularities in the surfaces, which will definitely bring the body to the rest. So, students, can you tell me that why the body is moving when the force is not there? Any student?
It is on a slope.
No, it's not on a slope. It's on a horizontal plane. Any student can tell me why the body is moving, which is compelling the body to move. Nobody? So that is defined in the first law of motion. What is the driving factor for the body? Is inertia of motion. This inertia of motion developed in the body. Because of this inertia of motion, the body keeps moving till infinity. So this case is covered. This case is also clear. So this is a hypothetical case, right? It's a hypothetical case. Uh, and this is practical case, right? Okay, so we know what is work done. We have understood what is work done in physics. And sometimes, normally you might feel that, if there's a wall and if a person is pushing the wall, a person is pushing the wall, right? So, you say that you have not done any work, he'll be angry with you because he might be sweating after some time. But according to you, according to physics, the work done is not not there. All right. So what appeals to your common sense is not justified by the physics. Okay. Sometimes. Okay. Another thing comes the unit and definition of work done. So, students, uh, work done, we all know, is equal to force times distance. Force times distance or displacement. Okay, force times distance is work done. Now, let's talk about units of all. Remember units, students, whenever this is like a equation, it has a equal to symbol. And the equation on the left hand side and on the right hand side, the units must belong to either CGS system or FPS system or MKS system or SI system. All right, so mostly in our lectures, we'll be using SI systems. You'll find most of the books in SI system across the world, except few countries, European countries, which go for FPS system. Very old books, which might have been written in CGS system, centigram, centimeter, gram, second, foot, pound, second, meter, kilogram, second, here also meter, kilogram, second, but some more fundamental units added like luminous intensity, etc. So students, now we'll talk about SI units. So force, anybody can tell me in SI unit is what? What is the unit of force in SI unit?
Newton.
Tell me.
Newton.
Newton. All right. And what is the unit of distance in SI units?
Meter.
Beautiful. So Newton and meter. Okay. Now this is equal to work done. Now, what is the meaning of this Newton and meter? Now, let's try to understand. Uh, Newton and meter means, let's say we have a book. Okay. We apply how much force? How much force? 1 Newton. 1 Newton can be written like this, and meter can be written as 1 meter. Am I right? How much force you're applying? 1 Newton. And 1 Newton is able to displace a body till how much distance? Tell me.
1 meter.
Beautiful. 1 meter. If 1 Newton force is applied and 1 Newton force displaces a body by 1 meter, the work done is said to be anyone? 1 J
Newt. Joule.
E, joule. Some people call it joule, some people pronounce it joule. Doesn't really matter. Languages don't matter. The depthness of concepts, what is matter. So somebody says define joule. So you will say whenever on a body 1 Newton force is acting, so that a body gets displaced by how much distance? 1.
1 meter.
The work done is said to be, students, 1 joule. Now,
Joule.
more depth in this. Students, have you seen in the units of work done, mass is not there? Okay, but indirectly, if you say Newton, if you talk about force, force is equal to, according to second law of motion, mass into acceleration. So in a way, mass is there, right? Work done too depends upon the mass, and force depends upon mass. So now let me ask you a question. Students, if I have 10 kg of mass, obviously it's 10 times more, and I'm moving it by 1 meter. Or if I have 1 kg of mass and I'm also moving it by one distance, so is the work done in both the cases same? No. In the first case, the work done will be, the mass is 10 kg. When the mass is 10 kg, you know, so students, in order to move 1 kg mass by 1 meter, or in order to move 10 kg mass by 1 meter, students, you know, you can say the work done is 10 times more. So 1 kg mass, you know, obviously to move it by 1 meter, you need 10 times more force also. So you can say like this, that here the force will be 10 times more. Here the force is, 1/10 of the force you need to move this one. So the work done will be 10 joules in first case, and 1 joule in the second case, imagining that corresponding to 10 kg I have applied 10 newton of force, and thinking 1 kg mass corresponds to 1 newton force. Okay, another thing, there may be little doubt or confusion in what I've explained, but it will be clear. See, students, I take another horizontal plane and I take another book. All right. So this is a book. Now I want to apply, 10 Newton force. 10 Newton force has moved the body by, let's say, half meter. How much work is done? So work done formula remains always same. Force times distance. Force is 10 Newton. Distance is half meter. That is equal to 5 Newton
Mm.
meter equal to 5 joule. All right. So from this we can understand, if 10 Newton force has moved the body by half meter, and suppose the same force 10 Newton doubles the distance, the work done will also get double. It will be 10 joule. Still another question, students. Uh, Suppose this is a body. Okay, I apply some force. Let's say the force is 2 Newton. In order to do 100 joule of work, by how much distance should I move the ball so that the work done is 100 joule? Anyone?
50 meters.
50 meters.
How much? 50 meter. All right, that's really great. So this is the definition of 1 joule, a force of 1 Newton displacing body of any mass. Students, now the mass of the body is not important, whether it is one mass or how much mass, you don't know. There's some body, and that body is being applied by how much force? 1 Newton. As a result, that body moves by 1 meter. We can say the work done is 1 joule. Now, from this, there's another question which arises. You might ask, sir, suppose there is a body of mass 1000 kg. It's a big body. It's a body like this, sitting on a table or on some platform. So, can you say, sir, that you can apply 1 Newton force on this and move it by 1 meter so that you can say the work is 1 joule? So, can anyone answer this? A student is asking this question, sir. There's a body of 1000 kg mass, or you can say 10 quintal. 10 quintal mass. So can you say, a student is asking, we can apply a force of 1 Newton and it moves by 1 meter and the work done is 1 joule? On the other hand, let us say there is a body of only 1 kg mass, and there I apply a force, and let's say 1 kg corresponds to 1 Newton. Just imagine. In order to move 1 kg mass, imagine 1 Newton force is sufficient. Imagine. And then the work done will be 1 joule. No, here the thing is 1 Newton force actually will not be able to move this 1000 kg mass. So it will not be able to do even 1 joule of work. It will not be able to do. So now if you want to work done, you need a bigger force. You need a bigger force, maybe 1000 Newton, maybe 10,000 Newton, I don't know. So when 10,000 Newton, let's say, force is being applied on this, and this moves by 1 meter, I will say my work done is 10,000 joule, or I can say 10 kilojoule. So good students, this is the unit of the work done and understanding of work done. At the same time, I have a natural attempt to ask you students, can you define 1 Newton force also? Anyone? Whenever somebody asks you to define something, think about the formula, how you will get that. 1 Newton is one force. Force is equal to mass into acceleration. From this you will get the unit. If mass is 1 kg and if acceleration is 1 meter per centimeter square, force will be 1 Newton. So what will be the definition of 1 Newton force? If some push or some pull, ultimately force is push or pull, is able to induce an acceleration or deceleration. Both. It can increase the velocity, it can decrease also, of 1 meter per second square in a body. I can say the push or the pull is worth force of 1 Newton. Once again, 1 Newton force is a force which induces an acceleration of 1 meter per second square in a mass of 1 kg. So from here, your previous doubt may be clear that imagine, student, if the mass is 10 kg and you want to accelerate 10 kg by 1 meter per second square, see, obviously it will come to your mind how much force will be required. If you want to accelerate 10 kg of mass by 1 meter per second square, how much force you have to apply? Tell me,
10 Newton.
tell me loudly.
10 Newton.
Beautiful. You have to apply 10 Newton. If you
10 Newton.
want to accelerate 50 kg of body by an acceleration of half meter per second square, how much force you have to apply?
25 Newton.
Beautiful.
100.
Beautiful, Hamza. No, not 100. You have to apply only 25 Newton force. Why? Because force is MA. So 50 into 1 by 2 is not 100. That is
Okay, sir.
25. Guys, this is about, you know, work done. Given you a small lecture today, and tomorrow's lecture, we're going to prove that work and energy both have same units, and never do the mistake of confusing energy with power, which has a unit of watt. The watt comes after a great physicist and an engineer, a young guy who used to see his dadima making chaya, and the steam in the chaya uplifting the lid going up and down, up and down. The idea came, if the steam can do some work on this lid, we have just understood what is work done. Work done is force times distance. James Watt could observe right in his childhood, not after this homework, not after lengthy assignments, not after timely submission. These people have different brain and they are hungry only for concepts, not for recognition, which 99% of teachers like me and students like you are hungry about. Not for concepts, but for recognition. You want to have marks, you want to have grade only for recognition, not for concepts. Then you have a different life, and then people follow you. So James Watt used to see that the lid is doing tung 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 tung. The lid is going up and down. Why? He used to ask his daddy, "I don't want to have tea. Why it's going down, up and down? Who is doing the force? Who is applying force? Who is doing the work done?" And daddy mom must be telling him, "Hey, come on, shut up." But ultimately, that was a James Watt who didn't really coin the theories, but the thermodynamic subject was, it came into being because of James Watt. He is a person, along with other people also. He built his first railway steam engine. Great guy. And one more interesting thing I'll tell you about this, students. Always in the world, there is theory and then there is practical. But in case of James Watt, he made the steam engine first. Yes, there were other physicists, engineers, and other people, but I'm not remembering them before James Watt. He read them, he took help from them, then his own curiosity, he made the steam engine, and after making the steam engine, then came the theory about thermodynamics. Things are very great. In the next lecture, we're going to see What is correlation between work and energy, and how power is different from work or energy? Rather, how power is associated with energy or work. So very simple, students. If you have energy, you can do work, and how fast or how slow you do the work with given amount of energy decides how much power you have. It's like in Hindi you say, if a boy is patla, you know, don't underestimate him. And if a boy is mota, don't fear him. Why? Because the mota person may have more energy but might have less power. You might win over him. Thank you very much. If you like the video, do not mind sharing it with your friends. Why? My YouTube channel grows. See that again, recognition, and more people think more in depth at your ninth level about the subject. That's a real recognition. Thank you very much.